All right, let's get started. So today we first of all going to discuss a little bit more about concurrency control. And for the past couple of lectures, we have been mostly discussing about concurrency control methods that use locking. And in the last lecture, we have started discussing about concurrency control methods that work without locks. And depending on the scenario, that can have performance advantages because we save the overhead for lock management. The last time we have already discussed two of them. First of all, oops, I cannot advance the slides here. All right. So first of all, we have been discussing about optimistic concurrency control, which essentially assumes that everything goes well and then checks at the very end. And if it is wrong, we have to abort and restart the transaction, but otherwise it is very efficient. Then we have talked about timestamp-based concurrency control, where we essentially associate objects with timestamps indicating when they were read or written for the last time. And those object timestamps are based or are derived from the timestamps of the transactions. We assign them to timestamps at the beginning, and then we try to simulate an execution in that timestamp order. Now, in the following, we're gonna discuss about two more concurrency control methods that work without locking. And both of them actually use different object versions. We have quickly discussed this slide last time. I'm gonna start here again. And the concurrency control method that we will discuss about is called multi-version concurrency control. And as the name suggests, the main idea is that instead of one version of an object, we might have we will keep multiple versions of an object that are associated with timestamps. And to see why that can be helpful, we have a little example over here. So if you look at the schedule that is marked here in the third line, we have a non-conflict serializable schedule. There is a conflict between transaction 1 and 2 on the A object at the beginning. So in the conflict graph, you would have an edge from 1 to 2. And later, there is a conflict on B as well. So in the conflict graph, we also have an edge from transaction 2 to transaction 1. And that is why you have a cycle. So it is non-conflict serializable. Now, this would not happen had we read the B object a little bit earlier for the first transaction. So if you imagine that we are moving this read of B by transaction 1, which is marked in blue, a little bit earlier, then we wouldn't have the cycle in the conflict graph. And maintaining multiple versions of object B gives you essentially that possibility, because once transaction 1 is requesting to read an object from B, in that case, we could just serve it the previous version of object B before the write by transaction 2 has happened. And because this is the conflict that is causing the cycle in the conflict graph, if we resolve it, we get a serializable, conflict serializable schedule again, right? So that is the idea behind the multi-version concurrency control. We essentially eliminate conflicts by serving older versions of an object, which of course requires us to keep around those multiple object versions. So this is the high-level outline of the multi-version concurrency control protocol. First of all, each transaction gets a timestamp when entering the system. That's a unique timestamp, and we try to make everything look as if those transactions had executed in the order of those timestamps. Whenever a transaction writes an object, in other concurrency control protocols, it means that the old value is overwritten by the new value. But in this case here, it means that a new write creates a new version of an object. First of all, before the transaction is actually allowed to write something, before we allow that to happen, we perform a check, which I will describe in more detail on the next slide. If the check fails, then the transaction actually has to be aborted. But if the check succeeds, then the transaction proceeds and creates a new version of the object. And the creation timestamp of that version, that is equal to the timestamp of the transaction. Because logically, we want to make everything look as if each transaction had executed precisely, atomically, at its timestamp. And therefore, if the transaction had really created the object, then it should get the timestamp of the transaction. Whenever we have a read, we can exploit the fact that we have multiple versions. So we choose which version we want to show to the transaction. Whenever a transaction that has timestamp I tries to read an object, then we serve the version of the object that has the largest timestamp, which is still smaller than I. And that is logical, because if transactions had really executed at their timestamps, then of course the transaction with timestamp I would see the last written version of the object. And that is just the version with the largest timestamp that is still smaller than the transaction timestamp I. All right. Now, I have mentioned a write check on the last slide. And this is a test that we do whenever a transaction tries to write an object. As always, we have to be consistent with the timestamp order of the transactions. So now let's assume that a transaction with timestamp I wants to write to an object A. Now, logically, if there is another transaction with a higher timestamp than I, then that other transaction, when reading object A, should have read the version written by transaction I, or even a later version. But for sure, it wouldn't have read an earlier version, because at the time I, the transaction which is currently being checked would have written the object with a timestamp of I, right? So here, basically, if we find out that there is currently a transaction with a higher timestamp than I, and that version has already read object A, then we must abort the check transaction, because if it had written the object at timestamp I, then the later transaction would have read that value or a later one. So if we would allow the transaction to proceed, it creates an inconsistency. All right, so that is the write check, and we perform it whenever a transaction tries to write an object. And in order to perform it, we need to not only keep track of the time at which objects are created, but also we have to keep track of the last read timestamp for an object. All right. So what we have seen so far, it serves to create conflict serializable schedules. We have seen in the last lectures those two hierarchies for schedules. The first one was about serializability. The second one was about abort-related properties. So what we have seen so far for multi-version concurrency control, essentially only deals with serializability, but it doesn't give you any abort-related properties. For instance, one important property is that the schedule is recoverable, because we don't commit a transaction before other transactions it has been influenced by have committed before. And the protocol we have seen so far does not yet take care of those properties. In order to get them, you can, however, extend the protocol and, for instance, delay commits until all influencing transactions have committed. So just so you know, if you ever choose to implement it, then you probably want to take care of those properties as well, and that requires some extensions to the protocol. So that was a short overview of a multi-version concurrency control. And now we are going to see a little bit of a different variant of that, which is also very commonly used in practice, and that is called snapshot isolation. Now, snapshot isolation essentially means that whenever a transaction starts, we are conceptually taking a snapshot of the database, which contains for each object the value of the last committed transaction. And then those transactions, they essentially operate on this frozen snapshot. So in a way, here we also keep around multiple versions of the database, but whenever a transaction starts, then it gets this frozen snapshot of the database, which doesn't change over time. With multi-version concurrency control in principle, while the transaction is executing, the values of different objects could change and new versions could be added. Here that cannot happen. So when reading data, transactions rely on the snapshot of the database that has been taken once they started executing. When writing to objects, in this case, we have to pay attention if multiple transactions are trying to write to the same object. If so, we could create conflict, so we cannot allow this to happen. So in this case, essentially, after a transaction has executed, we are checking in order to make sure that no other transaction was already writing to objects that the current transaction is trying to write to. If that is the case, then the current transaction can go ahead and commit. But if there has been overlapping writes to the same object by a concurrent transaction, then essentially the first writer wins and the other transaction has to be aborted in order to avoid conflict. Now, this may sound great, but there's a little catch to it. Let's make an example with two tables, A and B, which both have one integer column. And now imagine those two transactions that we see here. The first transaction essentially tries to insert the count of rows in A as a value into B. And the second transaction tries to insert the count of rows from table B as a value into table A. And now we assume that both of those transactions start at the same time, which means that they will operate on the same snapshot of the database. Now, imagine that those transactions execute and insert their values. Does anyone have a suspicion about whether the result of that can be equivalent to a serial execution of those transactions? If you have an opinion, please put it into the chat. All right. And here we have the suggestion that one of the inserted values will be one less than it should be. Okay, very good. All right. Let's analyze that in a little bit more detail. Let me move the chat around. Okay. So if we want to find out whether we get to a result that could have been generated by a serial execution, then maybe first of all, we want to think about all the possibilities for serial execution. So here we have two transactions. So we have a choice about which of them we execute first, and that creates two possibilities. Now, for instance, we could start by executing the first transaction. So the first transaction executes the query which inserts the count in A into table B. And assuming that at the start, those two tables are empty, we would insert a 0 into table B. And now we have one row in table A. So if the second transaction runs, which inserts into table A the count of rows in table B. So since we just inserted a row into table B, it means that we would now insert a 1 instead of a 0 into table A. If we do it the other way around, if we start with transaction 2 would first of all calculate the number of rows in B, which initially is 0, and insert that into A. So this is why in A we have now the 0. Now the first transaction runs and it inserts into table B the count of rows in table A. And since we have just inserted a row into table A, it would mean that we insert a 1 into table B. Now, if we use snapshot isolation, it means that both of those transactions start from the same snapshot of the database. And in this snapshot, both of the tables are empty. And since both of them execute concurrently on the same snapshot, it means that both of them will account 0 rows for both of the tables, and then they will insert the 0 into those two tables, A and B. And that is an anomaly that is called write skew. All right, so this is maybe something that is worth having another look at if that seems strange. But here we have definitely a behavior that couldn't happen if executing transactions one after the other one. Now, write skew is one example for an anomaly that isn't really mentioned in those anomalies that we have seen initially. The anomalies that we have seen initially, they are based on the SQL standard. And the fact that there is some concurrency control protocols which have anomalies that are not really mentioned in the standard has actually led to criticism of the SQL standard. So that is maybe the last thing that I want you to know about concurrency control, that we have seen those different SQL isolation levels, but depending on the system, for some of those isolation levels, you might actually still have some anomalies such as write skew, which are not mentioned in the SQL standard. But if you are running your database system with an important application, they might still lead to problems. So be very careful when using your database system in practice. Make sure that you understand well not only which isolation level you're dealing with, but also how precisely that isolation level is implemented and whether there might still be some anomalies that could appear. All right, so that was concurrency control. We have mostly been talking about locking-based concurrency control, and now we have also talked about a couple of alternatives without locking. In practice, locking-based concurrency control is very common. This is why we have spent more time discussing that. But as you have seen here, there's also many alternatives, and which one of them works best depends on the particularities of the scenario. All right. So we will now switch to a different topic. I'm gonna switch the slide set. If you have any questions about concurrency control currently, please feel free to put them into the chat. All right. Seems no all too urgent questions for the moment, so we will directly dive into the next topic, which is about recovery after system crashes. This is the component that we will be talking about. That is the recovery manager marked up here, and the relevant chapter in Ramakrishnan and Gerke, that is chapter number 20. So We have talked about the guarantees that database systems make when it comes to transaction processing. Atomicity, which means no partial executions. Consistency, which means that your data remains consistent and satisfies all constraints. We have talked a lot about isolation, which means we simulate different transactions executing serially. And finally, we have durability, which means that we do not lose data that belongs to committed transactions. Now, the recovery component essentially takes care of those two properties. First of all, atomicity, and then durability. So what we essentially want is this. So if we assume that we have multiple transactions executing in our system, and then suddenly a crash happens. And a crash could happen for many reasons. One of the reasons, for instance, is a sudden power outage, but it could also be other things such as a hardware fault or perhaps a software bug that suddenly makes the system crash. But in any case, we are currently executing lots of transactions, and then suddenly something happens and the database server has to shut down. Now, in this graph, basically, we have some transactions that have already executed, by which I mean they have already committed. So we have informed the user, this transaction has executed, you have nothing to worry about, and the effects will be persisted. And because of that, for those transactions that are now marked in green, we want to make sure that the effects of those transactions, they are actually persistent and will be recovered once the system comes back online. On the other side, for the transactions that are running during the crash, for those transactions, we want to abort them, and we want to essentially undo them such that no traces of those transactions remains in the system. This refers back to the atomicity guarantee, right? So this is what we want to achieve once the system comes back online after the crash. This is a little reminder here of the memory hierarchy. And the memory hierarchy makes it difficult to achieve the behavior that I have just shown. Because in the memory hierarchy, we have essentially two parts. We have a volatile memory, which will be erased if there is a sudden power failure, for instance. And we have non-volatile memory, such as hard disk, which will remain, where the content will remain, even during a system crash. Of course, from the safety perspective, we might choose to always write to a non-volatile storage. But of course, that would be very slow because, as the memory hierarchy shows, there's a higher level of the memory hierarchy which are volatile. They are at the same time much faster than the lower levels of the memory hierarchy. And for performance reasons, we therefore must work even with the volatile levels of the memory hierarchy. And that makes it challenging to guarantee that even during a crash, we won't lose any important data or end up with the effects of half-finished transactions in our system. Let's first of all discuss about challenges related to durability, which essentially means we guarantee that the effects of all committed transactions persist even if there is a system crash. Now, initially, once the transaction change data, their changes are written, first of all, to pages in the buffer pool. And as we have seen, the buffer pool, that is the main memory portion that is essentially reserved to the database system. And since it lives in main memory, it means it is volatile. And once the power cuts, all the content of the buffer pool will be lost. Now, one thing we could do, of course, is that every change is not only written into the buffer pool, but we also write it to hard disk. And if you do this immediately, or at least before the corresponding transaction commits, the problem is that we might get pretty bad performance because we have to write a lot of pages on hard disk. And on most of those pages, we actually have only very small changes because those transactions, they typically just change the data maybe in one row of your table, while they leave the other rows in the table unchanged. And that means if you're trying to immediately write those data pages from the buffer pool onto hard disk, then you're writing a lot of bytes, where most of them are actually unchanged, but just a few bytes have changed. And for that, you're actually performing a lot of page writes, and that is very inefficient. So here the naive approaches don't work well. So in the following, we're going to see a way to improve over that. First of all, let's discuss about atomicity, which essentially means we guarantee that no transaction is partially executed. And one easy way to guarantee that even during a crash would be just to leave all those changes to the data of a transaction in main memory. So we only change things in a buffer pool, and then we know if there's a crash, then the buffer pool is erased. So automatically all the changes by the uncommitted transactions are erased, which is actually quite convenient. And that would be an easy way of getting atomicity. The problem with this approach is this. Each transaction might change multiple pages. So if you want to avoid that those changes get written to hard disk before the transaction commits, it means that the transaction has to hold on to all of those pages in main memory until it commits. And that means that each concurrently executing transaction might have to hold many pages in main memory at the same time. And that means we cannot execute too many transactions at the same time. And all of those things that we discussed about concurrency control, a lot of it was exactly about allowing as many transactions as possible to execute at the same time in order to increase the throughput of your system, meaning the number of transactions that get finished per time unit. So if you would introduce a constraint that transactions have to reserve many pages in main memory, since the amount of main memory we have is typically limited, it would mean that we limit the number of transactions that can execute at the same time, and therefore our throughput, which is something that we want to avoid. So the alternative to that is, of course, that we allow transactions to let go of their pages in main memory, and therefore we have more flexibility about how we use those precious pages in main memory. We essentially allow ourselves to swap those pages in main memory between different transactions. The problem with this is the following. So if a transaction has performed some changes on a data page in main memory, and now we want to assign that page, we want to lend that page to a different transaction, which needs to do something else. So at that point, of course, if we simply erase the current page in main memory, it would mean that we would lose the changes by the transaction, which because of durability, we obviously don't want to do. On the other side, if we choose to keep the changes, and since we don't have that much main memory, we need to write those changes to a different layer in the memory hierarchy. So typically, we would need to write those changes to hard disk. Here, the changes are persistent. So if the current transaction successfully executes, then we are okay with writing those changes to hard disk. But if the current transaction suddenly aborts, or if there is a crash so that the current transaction is implicitly aborted, then it means that now suddenly on hard disk, we have the changes by some half-finished, by some aborted transaction, and that we don't want to have due to atomicity. So again, there is different naive solutions, but all of them come with a serious drawback. So in the following, we're going to see how we can improve over that. I think there might have been a question in the chat. Let me quickly check. So the question is whether in the alternative we are writing directly to the database data. So I have pointed out multiple alternatives for durability and for atomicity. And indeed, one of them was that we essentially directly write changes to our database data so we directly can write changes to a hard disk, and that has the advantage that they persist even after a system crash, which is good if the transaction is committed. On the other side, if the transaction doesn't finish before the crash and must be aborted, it means that we now have changes on hard disk that belong to a half-finished transaction, and we need to sooner or later undo those changes again. All right, so this here is a summary of the different options that we have and that we have essentially discussed in the previous slides. So we can choose to use a so-called a force policy, which means that we make all changes to the data persistent on hard disk before the corresponding transaction commits. The advantage of that is that we are safe from losing data in the case of a system crash. The disadvantage of that is that we have a lot of page writes by each transaction, and that leads to poor response time. The other the other choice that we have is how flexible we are in assigning buffer slots to transactions. A no-steal policy essentially means that each transaction must hold on to its pages in the buffer pool until it commits. The advantage of that is that we don't have to deal with undoing changes on hard disk by aborted transactions. The disadvantage of it is that each transaction will actually consume a lot of main memory pages, which severely limits our transaction throughput. So for performance reasons, what we want is a policy that allows a stealing, which essentially means that one transaction can steal a buffer slot from another transaction before the other transaction is actually committed. So allowing stealing leads to a higher throughput, and having a no force policy, which means we do not force transactions to write all the changes to hard disk, that leads to better response time. So for performance reasons, we want to allow stealing, and we don't want to force writes to hard disk. The problem with that is, of course, what do we do about durability and atomicity guarantees? Now, the high-level solution that we will discuss in the following, that is logging, which essentially means that we don't write the actual data on hard disk, but we write a highly compressed representation just of the deltas, of the changes to the data to hard disk. And this is what we call a log. Now, in the following, we're going to discuss in more detail about how logging can help us to resolve those performance challenges that I have discussed on the last slides. Now, if we want to guarantee durability, it generally means that we have to make changes persistent of a transaction before the transaction commits, because durability means that after the transaction commits, it is guaranteed to stay in the system even if there is a crash. And very clearly, since everything in volatile memory is lost during a crash, we must make changes persistent on hard disk before we allow a transaction to commit. We have already discussed the possibility to update the actual data before the commit, which is what we call the force policy. The reason why that is inefficient is that the changes that a transaction needs to make, they're typically distributed over many different data pages. And this means that we would actually have a lot of page writes just for making persistent a lot of small changes in the data. The idea behind logging is that we don't do that, but instead we just collect all those updates to the data in a very compressed representation. So for one transaction, you typically can collect all its updates in compressed representation on one single log data page. And if we want to make that persistent, we can just write the log data to hard disk, typically with one single page write. And that is much more efficient than writing all those different data pages that the transaction has changed. And then we just have to make sure that this logging related data are written to hard disk before the transaction commits. And so even if we haven't changed the actual data, since we have a list of the updates to the data, that is sufficient in order to recover the data if there's a crash once the system comes back online. Now let's see how logging can help us to deal with atomicity. Now, we have already discussed why we want to swap pages in the buffer pool between different transactions. And once we swap ownership of one slot in the buffer pool from one transaction to another one, we first of all have to preserve the changes of the first transaction. And that means that we need to write the current content of the buffer pool slot to hard disk. Because otherwise the changes would be lost, and that is incompatible with the durability requirement. So the thing is this: if we swap pages and we write changes to the current page by the current transaction on hard disk, if the current transaction later aborts, which could, for instance, be because the system crashes, but also because of a different reason. In that case, we need to take care of those changes to the data that we now have already written to hard disk, because we need to undo those changes in order to guarantee that the database looks as if the aborted transaction had never happened. And in order to enable this, we will expand our log with information that allows us to undo each change to the data in case the corresponding transaction aborts. And we just have to make sure that we write those log entries for a specific page to hard disk, which means that if the system crashes immediately after we have written the current page content from the buffer slot to hard disk, then we still have the required information in order to undo the changes by the current transaction in order to bring the data back into a consistent state. So now we have discussed how logging can help with durability and atomicity. The general term for the class of logging algorithms that we will discuss about in the following is write-ahead logging. And the write-ahead logging is essentially characterized by the two rules that you see here. First of all, we have to write all the log entries that relate to a transaction before the transaction commits. And the second rule is we have to write all log entries that concern a page in the buffer pool to hard disk before that a page is written to hard disk itself. Rule number one is important to guarantee durability, because if a transaction commits and we have the log entries from that transaction on hard disk, then we can use that in order to redo the changes of the transaction, even if the system immediately crashes after the transaction commit. Rule number two is important for atomicity, because if we write a change data page to hard disk and those changes have been made by a transaction that will later abort, if we have the log entries about that page on hard disk already, then we can undo the changes in order to erase the effects of the aborted transaction. So this is the two rules of a write-ahead logging. And in the following, we're going to see one specific algorithm that uses write-ahead logging. This algorithm is called the ARIES algorithm. It is a very classical algorithm. It has been proposed decades ago, but the variants of it are still quite popular in database systems. Now, this algorithm uses a write-ahead logging, and we will see in the following how precisely it implements it. And after we boot the system up again after a crash, this ARIES algorithm will perform 3 recovery phases. It first of all will analyze the last log entries that it finds on hard disk in order to decide which transactions need to be undone and for which transactions we need to redo data changes. Then it will have the redo phase in which we redo the changes of committed transactions that were lost due to the crash. And finally, we have the undo phase in which we undo the changes of all transactions that have still been active during the crash and must be aborted. So we are going to see that in much more detail in the following. It is an algorithm that has quite a few moving parts, so we will take some time to discuss the different parts of the algorithm and the different data structures in this lecture and also still in the next lecture. In general, we're going to break it down into 3 phases. First of all, we're going to discuss about the data structures of the algorithm. Then we're going to talk about the behavior that it has at runtime, where it generates log entries that help with recovery later. And finally, we're going to discuss in detail about how recovery proceeds precisely. Now, in the following, we still have a little bit of time to talk about the different data structures of the ARIES algorithm. And all of those different data structures, I have them represented here. So here we have some data structures in gray, and those are the data structures that do not directly relate to the ARIES algorithm. So here we have, of course, the data pages on a hard disk, and we have the buffer pool pages in main memory. So you see the divider in the middle of the screen. Everything on top of it is stored in main memory, which means it is volatile and will be lost during a crash. Everything below the divider is stored on hard disk. It is non-volatile and will persist after a crash. So here we have data pages on hard disk in gray, and we have buffer pool pages in main memory in gray. Now, the first thing that I want to discuss here is you see those little blue rectangles for the buffer pool and for the data pages. Those are essentially timestamps that tell the ARIES algorithm when those pages have changed for the last time. Beyond that, there's a couple of specific data structures of the ARIES algorithm here drawn in blue. The following, we're gonna go over all of those different data structures and explain at a high level what they are about. Now, first of all, log entries are first written not to hard disk, but into main memory. We postpone writing them to hard disk for as long as possible. And the log tail is stored in main memory. And those are essentially the most recent log entries which have been generated, but which haven't made it to hard disk yet. So this log tail, those are log entries which are eventually written to hard disk unless there's a crash, because in that case, the log tail is essentially lost. The flushed LSN keeps track essentially of where the log tail starts. So using the flushed LSN, we keep track of which log entries have already been made persistent on hard disk. So this essentially captures the LSN, which stands for the log sequence number, and that is a unique identifier for the line in the log file, essentially. And the flushed LSN, that is essentially the last log line that made it already to hard disk. So in several cases, it is important to verify whether log entries, for instance, about a transaction have already made it to hard disk, because then we can allow that transaction to commit. And the flushed LSN essentially keeps track of which log entries have already been made persistent. Now, the log tail is essentially a buffer, and in the context of buffers, we often use the word flushed in order to say that we essentially write the buffer content to a persistent storage, and then we erase it to make it available again and enable it to receive more data. And this is why we use this terminology here when it comes to the log. So the log tail is a buffer, and every once in a while we flush it, meaning we write its content to hard disk, and flushed LSN keeps track of when that has happened for the last time. Now, here on hard disk, we have the actual log that will be used for recovery. It is stored on persistent storage, so after we come back online after a crash, we will be able to access those entries here. And the recovery phase of the ARIES algorithm uses exactly this log in order to bring the data back into a consistent state. The transaction table is an auxiliary data structure which keeps track of transactions that are currently active. For each transaction, it stores the current status, whether the transaction is currently running or whether it has already decided to commit, for instance. And also for each transaction, we keep track of the last log line, of the last log sequence number that this transaction has generated. I see there's a couple of questions in the chat. Let me quickly bring the chat back. Okay, very good. Okay, so here there was a great question and already the answer. So LSN stands for log sequence number. So you can imagine that all those log entries, they are numbered essentially. Each log entry has a unique number, and this number is monotonically increasing. So if you imagine your entire log as a text file, for instance, then the LSN would essentially be the line number. And we keep appending lines to the end of that file. All right, so that is the transaction table, and we also have a so-called dirty page table, and that essentially keep track of the pages which are currently loaded into the buffer pool in main memory, and they have been changed in some way, and those changes have not yet made it to hard disk. So this essentially keeps track of pages that might be potentially problematic, because I might lose changes to those pages which have only been made in main memory, but haven't been persisted on hard disk yet. All right. And as I have already said here, associated with each slot in the buffer pool, we have the log sequence number of the last log entry, which changed the corresponding page. And we also have the same on hard disk. So this is a high-level overview of the different data structures that the algorithm uses. So here you see already there's quite a few different data structures. And in the following, we're going to see in more detail how the algorithm updates those data structures at runtime and how it will exploit those data structures during recovery. So this is what we are going to do next time. And in the following, probably in the following 2 lectures, we will keep discussing about this algorithm. Have a nice day, and then I see you again on Wednesday.